This video is going to outline the new features found in Adapt Builder 2019 Build 0. This will include a summary of the main features. Any bug fixes or secondary features that have been included are summarized in the log file found in the Program Files folder for the program. We're going to be referencing the Adapt Builder 2019 release notes, and we're going to go ahead and start with second order Pdelta analysis. In this image, you can see we have a multi-story frame structure. It has columns, walls, slabs. There is a transfer level where we can see beams and a few ramps. We'll talk about ramps later on in this video. We're going to go ahead and go to loading. Under load combinations, a user can now designate a combination as Pdelta. In this example, we have 3 Pdelta combinations listed here. There's a new analysis and design option type for Pdelta, and you can see that here in this pull-down list. The program will process Pdelta combinations either as a batch, when you have repeating combinations, load cases included in those combinations and factors. So for example, we have PDM1, this stands for Pdelta Master 1, and this has factors of 1 for all of our gravity load cases. Pdelta SX is for seismic in the X direction, and SY would be seismic in the Y direction as a simple example. Those also have the same identical factors for the gravity load cases. The only difference is they also have an extra load case included, 1 times EQX and 1 times EQY. Because these 3 sets of factors and load cases are identical, this first combination is designated as a master combination, meaning the program will generate a geometric stiffness matrix from that combination and then apply it to the solution for these 2 combinations. If you want the program to uniquely solve each Pdelta combination separately, we would remove the master combination from the list, and we would only solve for Pdelta SX and SY. Each would allow the program to solve its own unique geometric matrix and then produce a solution for these 2 combinations. So these 2 combinations are sourcing this combination for the production of that matrix. In designating Pdelta as the combination, the program does not design design strips for Pdelta solutions. Those are suppressed. The user can evaluate analysis results, which we'll talk about later, for Pdelta in terms of drift amplification, and also moment amplification for columns. The user can design columns relative and walls relative to Pdelta solutions. So we've talked about how do we set up second order Pdelta analysis combinations. The next thing we want to talk about are results that are generated for these combinations, and those are drift and moment amplification factors. That's the second thing we'll talk about. We'll go back to our model. We've solved this frame for Pdelta, and you'll note under the result browser in the loads tab, there's a new branch called Pdelta, which allows us to select, just like any other combination, one of the Pdelta combinations. For example, for Pdelta SX, this is again seismic in the positive X direction following the global orientation for positive direction. If we select analysis, and I'm going to go over here to column design and look at only the columns, and we'll go ahead and go to single level. I'll navigate just to the top of the structure for simplicity. You can see for column results under drift, we now have options set for amplification of combined global drift, X direction drift, and Y direction drift. The amplification factor is the ratio of the second order drift to the first order drift. So the program gives us an indication of that for each column, and it checks it against a user-defined value which is defaulted to 1.4. That can be modified both for drift and moment amplification in these 2 options here. You can see this is set to 1.4. So coming back to the results, If, for example, I look at the X direction drift, the program will color code those columns which are acceptable and produce the maximum ratio um, relative to top and bottom displacements at the particular level for drift from second order and first order results. Those are just graphical results that can be had using these new options. Additionally, we have moment amplification factors about RR and SS directions. So the primary driver for seismic in the X direction would be bending about SS. We'll go ahead and turn that on, and we can see again we have moment amplification factors. The program produces a second order to first order ratio of moments at the top and bottom and reports the worst case here as a ratio. If it's greater than the threshold 1.4, it would be flagged as red. If we go ahead and turn on the entire system here, set of columns, you can see amplification. There's one location where it's flagging this as 1.44. If I go to the other direction and just zoom out, there's additional locations that are flagged. These are, again, just graphical results relative to those Pdelta combinations. If you select a combination that we would consider a regular combination, for example, under no code check, we produced essentially the same repetitive combos but without Pdelta. If we turn those on, you can see these are grayed out and the check becomes not applicable in the result tree. We're going to go back to our release notes document. I'm going to jump all the way down here to this option for drift reporting. This is linked to Pdelta and just drift in general. In the program, if we have run a global frame and checked drift graphically, there's also new options for drift output in XLS format. Under reports, analysis data, under drift report, the program opens a dialog. You have the ability to select the combinations you want to produce a report for. In this case, I'll produce it for just one combo. We'll do this for the Pdelta in the X direction for seismic. And we can also input our allowable that we want to check against within the XLS report. This has no linkage back to the graphical report, but it's only produced for the XLS report. And then the amplification factor, again, no linkage back to the graphical check. If we select the direction, we can look at unidirectional results X and Y separated or combined results. We'll just look at all three. I'll select OK, and the program will launch a new XLS report. Okay, and this is the report. There are several different sheets here. I'll describe each just in summary. We have stations which are referenced from top to bottom in the structure. So this will list all of the columns at each plane and the column coordinates along with the heights of those columns. This is a good reference if you needed to pull out coordinates of those column locations aside from just the drift reporting. The program also reports displacements for each of the columns. So you can see for each plane, each column is listed, the load combination is listed, the type and designation, and then we produce the displacements XY at the bottom and top, as well as the combined displacements. These are just raw displacement results for the combination that you had selected. Drifted columns, the program will show drift in X, Y, and combined in this case for the same combinations and the same column locations and the percentage. So this is the actual interstory drift, the differential drift for the direction or combined. This is the percentage relative to the story height, and this is checked against allowable. If any three of these exceed allowable, the program will flag it as no good or okay if it's less than allowable. The average drift takes the average of all columns at a level, so the program would report that per plane. You can see we have planes 2 through 28. This is again X, Y, and combined, the percentage relative to the story height, and then the code check versus allowable. Maximum drift envelope. This will just produce the report of the maximum drift in the X, Y, or combined direction against allowable. Average drift envelope, again, we look at reduced report for the average drift of all columns in the story. and then we look at the drift amplification factors. So for each column location, we have a percentage of drift amplification against an allowable. This is just a tabular format of what you might check more formally in graphical form. We're now going to switch gears and talk about the strip modeling editor, the dynamic editor, and how that has been improved. We'll also talk after that about splitters, how splitters are now redefined and used to allow for more efficient creation of design strips. So in this model, I'll go ahead and reset the view. We're going to go to single level mode, and I'll work down here to level 3, for example. At level 3, we're going to make sure that if you import a new or an existing file into the new program, our recommendation is to remove all splitters from that file. Leave your support lines, but remove splitters, because the definition and the use of splitters has changed quite dramatically from previous versions of the program. So in this case, we're going to go ahead and just delete the design strips. I'm going to turn on my splitters, and we're going to go ahead and select by type. I'm going to remove the splitters and the support lines. We're going to show this dynamic editor just in pure form, using it as if this was a newly created model. Okay, so we'll go to floor design. The new tool is located here under strip modeling as dynamic editor. Now the user can always generate design strips in X or Y directions using X and Y tools. This is similar to the previous version. You're not required to use the dynamic editor. For example, I can select X. I can go ahead and just create a strip like so. The program, in this case, since I started and ended the support line outside of the slab, it leaves that point there. So you may have to edit that if you want it to be a cleaner entry of the support line. I may have to use the snap to endpoint or snap perpendicular to pull those lines back. Okay, so these two tools work essentially the same as what you had in previous versions. If I now use the dynamic editor, there's 4 new tabs in the editor. We're going to start with the wizard. If we go to X direction, we're going to start here using our construction line, and as long as that goes through a column, it will scan and pick up that point as part of the strip. So if I end it here and press enter, it will truncate the support line to the slab edges and reduce it back. Same here, and notice I'm kind of just picking between the columns. Here I can put intermediate click points to change the direction of the construction line. If I click on the endpoints or near the endpoints of walls, it will scan that and pick up the 2 endpoints of walls, like so. I'm going to go ahead and just add one at that location. If I click near the endpoint for a perpendicular or a wall in the opposite direction, it will pick up those points also. Now notice what happened here. This ended the line there because I terminated that point. I'll pause it. I can just delete that. I can resume. So this pause resume gives you a nice capability of modifying support lines if you make a mistake. And then we have something maybe like this. Finally, we'll do 2 more down here in the X direction, like so. We're going to go ahead and close that for just a moment. Now, in previous versions, we would need splitters at a few locations. We would need splitters likely here. I would need a splitter wherever our support lines stop inside of the slab region. We would need these splitters, and then we might need splitters to bound off these openings. So we'll go ahead and leave all splitters out of this. I'm going to generate the design strips, and we can see the program can now more intelligently detect where the support line starts and stops, and it can produce the strips without any need of splitters bounding the edges, start and end of a strip. One thing that the splitter is useful for is being able to terminate the width of a design tributary based on just a simple input of a splitter. For example, I don't want this to extend into the opening, so I'm going to add a splitter just here arbitrarily and maybe there. We'll go ahead and delete the strips. I'll use my X splitter. I'm going to add a splitter there, and I'm going to add one here. Once I'm done doing that, I can generate the strips again. And you can see this strip, because it goes through this region, extends down to the splitter. This strip extends up to the splitter, and vice versa on the other side. Okay, I may need to add 2 more splitters to completely release the strips from extending over the openings. But again, the splitter input is quite simple. If we go ahead and just add 2 more splitters, maybe I add one here, and I add one there. And now we have a nice arrangement of design strips in the X direction. I could come back to the dynamic editor, and I'm going to now do the Y direction. So the Y direction might look something like this. I'll snap near this point, near that point. Same thing here, near one endpoint, one on the other side. And again, here I did not continue, so let me go ahead and make that modification. I'll just delete that. I'll resume. This is point 1, point 2, and let's say point 3 and 4. And then we might have one along there. And I'll close that. Now we don't need to see the X direction splitters here. I'll go ahead and turn the splitter view off. I may want Y direction splitters, so I'll preemptively add the Y direction splitters. We're going to add one here. I can have more precision if I use snap tools. I could maybe add one there closer to the wall. And then if I use the actual points of the opening, I can get quite precise in where the splitters are placed. Something like that. And we'll go ahead again and generate the strips. After producing those strips, we'll just isolate this Y direction, and now we have design cuts that look like so. So the new strip tools are very nice and very easy to use for generation of strips more rapidly than previous versions. One thing to note is if I was to close this model and I'll reopen the model, we're going to reopen this in RC mode. Okay, we'll go back to level 3. And if we go to criteria under analysis and design options, we notice that for conventionally reinforced only RC slabs, the middle strip option has been removed. And this was required to allow the new functionality to work as intended during the implementation. So for middle strips, the user would have to actually create support lines for those middle strips manually. But with the new wizard and new ability to do that, that can be done quite rapidly. So that functionality will likely be restored in a previous version, but in this first release, that functionality is removed from the version. So if I, for example, wanted to add middle strips in this X direction, I can very easily do that again using the wizard. I could just create strips like so. There's middle strip 1. We might have middle strip 2 there, maybe middle strip 3, 4. There's 5, and there's 6. In doing that, we get some layout of strips that may look like this. Okay, so middle strips can be done using the wizard or again manually through creating X and Y direction support lines. We'll go back to that dynamic editor, and the second option in the editor is limits. The program allows us to modify support line designations more quickly versus just going in and double clicking on a support line and changing the modifications there. So we can modify design criteria. For example, if I wanted to change this to one way, I would just change it through click once selecting this option. And you could also window select. So this gives you a little more control over modifying more than just one support line. You can also define tributary limits using this window, as well as a double click. If I pause this and I double click on this strip, these same options for tributary limits are shown under Design Section Options. You can see a few new things here. Number one, the program allows you to either enter the maximum number of sections per span or generate a maximum section spacing with minimum number of sections, which is the new default. Tributary width limits, if you wanted to limit the tributary per side, maybe I want to limit this particular middle strip to 2 feet per side, I would set that here individually, or I could set it through this option here in the dynamic editor right there. If we go back and generate the strips again, and I'll isolate that X direction, you can see that's been limited to that value. This does not stretch down, we just simply limit this to this particular value. Now if I put a splitter along here, the program interprets that splitter. So if I just say, well, I want to add a splitter along this path and regenerate the strips based on the splitter and that input for maximum tributary width, now you can see this cuts down to the splitter, this cuts down to the splitter, and this 2 feet still is imposed on that support line. I'll remove that splitter and let's set this back to none for the tributary width limit, and we'll just regenerate again to restore what we had previous. Okay, coming back to the dynamic editor, the third option here is walls. How do we go about generating section cuts near walls? You can see that there's some auto options here that are already set. This is pertaining only to the wall as how it's defined in terms of a boundary for design strips. So for example, this line here says it's a Y only boundary. I want this to be an X boundary. If I change this, for example, to X boundary, I'll just do user defined. I'm going to go ahead and click on that wall as an X boundary, and I'll close it. If I generate the design cuts, this is a mechanism used to allow the program to generate strips and how they interact with walls. So you can see this design cut here extends all the way down to the newly imposed X boundary, and there's a tiny gap between those. This allows us to control how support lines again interact with walls, so that we may not want the support line section to cut over the wall but just go right up to the face of the wall. So this allows control over that type of an arrangement. If we go back to our assignments here, if I want that to be an X and Y boundary, we'll go back to user defined. I want this to be X and Y. I'll click that. That changes it to X and Y. Now if we look at the other direction, okay, these design cuts that extend over this wall are now going to be trimmed back, because now it's also being used as an imposed Y direction boundary based on the rule that I assigned. So I can generate this again, and if we isolate the Y direction, you can see these cuts along that wall get trimmed back in that against that wall. Let's go back to dynamic editor. Again, this just allows you to control wall boundaries. If you don't want any boundaries for walls, you can always go through and just tag all of the walls as no boundary. Otherwise, the auto assignments would be generated. You can see there's a few no boundary. This, for example, is currently no boundary. This is currently user defined as an X and Y boundary, and then this is defined as a Y boundary only. So the last thing is display. We can just simply control display of properties of support lines using this option. So I can display the criteria, direction, limit, and if you update, it just shows us those different values on the different support lines. So just easier ways to control visibility of characteristics of a support line versus double clicking and having to go into the properties of the support line. One additional thing to point out regarding design strips is beams. How does the program treat beams when we use the dynamic editor to snap on beam locations? So we're going to add a beam along this line. I'll go over here to model and we'll just say I want to add a beam from point A to point B, and I'm going to delete this strip. I'll delete out the design strips for the model, and we want to talk about how is this beam treated using the new options for the dynamic editor. If I use my dynamic editor, and let's say I go from through this column, through that column, back through that column, and then over to the edge, and I'll just close that, you can see this is a continuous support line, and it takes on the characteristic of a two-way slab by default. So we would have to rely on previously implemented mechanisms to design that beam. The program recognizes that there's a beam there. It will design it according to beam requirements per code, but all of the reinforcement that's linked and used for the design of that beam, the sizes, are based on whatever settings we have under the criteria options for rebar size and material. So two-way slab, we have 5s and 8s. For beams, we actually might want to use, number 9s, for example. So the program, again, designs the proper amount of area of steel, but the rebar assignment to the beam, it takes on the characteristic setting of a two-way slab size. So these sizes here. If we want more explicit control of that being labeled as a beam, we can do that using the new editor. So I'll go back, and now I'm going to go ahead and just snap near the endpoint of the beam, like so. And in so doing, the program automatically breaks this up. This is now a two-way slab. This becomes a beam, and then we have a two-way slab. Okay, the beam characteristics can take on two additional options here. When we have a beam, we have now the option for effective flange width as beam criteria. So we've talked about the dynamic editor, we've talked about splitters. Now we're getting into the effective flange for beams. You can see this option here for effective flange that we just showed under the properties of that beam. Now to fully explore this, we're going to actually go up to level 6. This beam here, we've just manually created the X support line. We've labeled it as a beam design, and we are going to use the effective flange width option. What does this do? This allows the program to use the effective properties for the calculation of reinforcement for the design cut, as well as the stress component, the top and bottom flexural stress. If we look at simple bending theory, we might say the stress is equal to M over S plus P over A. Well, the section modulus used, or Y over I used, are those based on the effective properties of the beam section when this is used. The area is using the full flange based on the modeled design strip. So let's look at that a little bit more. If we generate the strips, we would consider this width from here to here as the full, I'll call it the full tributary, full T. When we design that strip, if I take that strip for example and I design those sections, the properties used for that particular section cut are going to be the effective properties, not the full properties, and that's reflective in the dialog that shows us the section cut properties when we design a series of sections linked to a support line. Okay, so coming back to this design strip, we can see under design sections the length is set to 163. The B effective is also 163. There's a little more precision in this number that's reported. If I go back to design section options, we need to make sure that that's actually updated before we apply it. Once it's updated, let's go back and design again just to see the reflection in the properties dialog. Okay, coming back to that, you can see now the The physical cut is 162, the effective flange is 122.8, and this follows ACI and European code implementations of effective flange. Those are outlined in more detail in the new features supplement manual, which can be linked from the help menu up at the top right. Okay, so this is a effective idealized section versus the full section. The actual moment that we see here, for example, in this case, we have a positive demand of 192.3. That is based on the integration over the full design cut. The design itself is based again on the effective properties. As the user, you can also designate whether or not you want to exclude or include the tendons and the reinforcement for the design of the section. So any reinforcement or tendons that physically fall outside of the effective width can be used or excluded depending on the user's input here. By default, we include them. The user can control whether they are excluded by these two selection boxes. For design strips, the program now reports graphical area of steel. That's this option here. Longitudinal reinforcement as area of steel. And in the program, the way this is represented is through use of the result browser. If we select a combination, for example, strength, dead and live, and we've produced the rebar plan, we've already calculated the rebar for that combination, we can now review calculated as required, calculated as provided rebar, any base reinforcement, and then the area of steel. For example, the required rebar for strength, dead and live is represented by these graphs. The green is top rebar, the blue is bottom rebar. If I turn on the calculated rebar plan, let's just go to rebar and display it. This shows us the actual bars on plan with the graph. So those should match in terms of location. If we go to provided rebar, this is what the program is actually adding as provided rebar in that section. So there may be cases where the required rebar and the provided rebar contain a gap. Like here, we need 1.58 provided, that's what we're adding to the slab, and we only need 0.9. That means that minimum reinforcement may actually control at that particular location. We can also, if we have any base rebar, show the base rebar and also the percentage of steel as a function of the section area along these graphs. The next two features we're going to discuss are ramp modeling and also beam offsets. This is a necessary improvement to support beams that are modeled at ramps. And to do this, we're going to go ahead and we're going to create a new instance of a model. Okay, and let's go and create just a simple model. I'll model just a slab and a few columns. And let's say in this we're going to have a ramp, maybe that goes from there to there. And we have the ability now to model ramps using this option found in Model, Add Structural Components. So this ramp, I'll say, starts at these 2 points, these columns here. So there's point 1 and 2. Those define the top of the ramp. The third point I'll say is here. And notice once we select the third point, this becomes locked. That allows the program to maintain just a planar ramp, which is a limitation where we have to model these as planar elements. So this becomes our ramp component. I'm actually going to move that column there, and I'll move this one just to the midpoint of the ramp, and this one also to midpoint. Okay, so we have this ramp element. A couple of things to note is under visibility, we can see the ramps if we go to a solid model. The program does not cut out the slab over the ramp. That requires us to add an opening. So we'll go here and just add an opening right on top of the ramp, like so. If I use the 3D view option here, top, front, right view, this warning will appear that just says that the view may not show the overlap of the ramps properly, so you may have to go back to that rendering. So looking at that, this is now what we have. If I go to our rendering, we have something that looks like that. It's just a simple ramp. It may be required for continuity of a lateral system that's a moment frame versus using workarounds. It might be more applicable to earlier versions of the software. So we've modeled this ramp. A couple of other things to note is any beam connected to the ramp or column can be offset downward and connect automatically to the ramp. So if I model, for example, a beam along here, let me make sure that snaps. And if I go back to my 3D view, that beam is actually modeled at this reference plane. If I select the beam, there's a new option under pre-processing that connects with the ramp. So that drops that down to the level where it should be intersecting with the ramp, like so. You can also drop columns down. So if I select, for example, this column and I use connect with ramp, this column would drop down as well. Okay, we can also model longitudinal beams along the length of the ramp. If we had a beam, for example, that went from here all the way over to there, and coming back to this 3D view, that's also at the active plane, which is the current plane in this case. I can select this and align it with the ramp. Ramps can be copied just like any other component. If I select all of this, I can copy that using modify vertical copy up one time, and we now have two ramps, basically identical slabs. Let me make sure I'm in multi-level mode to view that, like so. The ability to slope columns or beams rather, in this case, requires the ability to support offsets at both start and end point of the beam. So for location, you now have the ability to model beams really as braces. You could apply this to something other than just ramps. You could have a sloped beam member in a model using these offsets. Okay, back under model, there's a third option relative to ramps, show ramp components. If we go to a single level, for example, this simply just shows the ramp components in isolation and connected components. I can always go back to the default display using this option for default display. So that isolates ramp components for viewing if you needed to quickly review how the ramp looks or how it's modeled. Now, for ramping, ramps number one cannot be designed. We can't add a support line and design the ramps, and also tendons cannot be modeled in ramps. So those are two limitations relative to ramps. It's important for the user to understand how that applies to design strips. So if we have a design strip, for example, that is along this path, number one, there's our first support line. Number two, we might have a support line along this path. The third support line might follow this path. That's 3, and then 4 down here. In this case, we do not want this to extend into the ramp, and that might lead to geometry. If we look at a section cut this way, that might lead to geometry where we have the upper slab and then the ramp slab. And when we combine this plus this into an idealized section, we may actually get something that looks very deep like that. It's just a solid chunk of concrete. So it's advisable for the user in this case to add splitters. We would add splitters, and we showed earlier in the video how splitters can be used and modeled very easily. I would just add a splitter along this, just slightly inside the ramp, there and there, or right on the edge of the ramp. And that isolates this area from containing any portion of concrete as part of the section cut. In future versions of the software, we will add the functionality to design ramps. In the current implementation, their main purpose, again, is just for an analysis element, mainly for, again, continuity of a lateral system. If you needed to include a more precise way of modeling ramps, we now have this component. There have been two new major improvements made to punching shear for Builder 2019, and these mainly include the ability for the user to check critical sections based on an octagonally shaped boundary or critical section. We have some code references here outlining this. For ACI, this applies only to ACI in the current implementation. All versions of ACI 3.18 in the program, that's version 14 all the way back through 99. And we also have included the ability for the program to check the minimum number or minimum rails, studs, or shear reinforcement for purposes of seismic drift. Again, a code reference is shown here. We're going to now show how these are actually implemented in the program. We'll go back to our main model that we were using previously, and we're going to stick with level 3 shown here. This is a post-tensioned level, so we have post-tensioning shown. We're going to analyze the slab. So I'm going to analyze this just for one combination, strength, dead, and live, just to produce a result that allows us to check punching shear. Okay, we'll go back to our default display. And under floor design, shear design, there are two new options, and I'll highlight these new options. The first option is to consider the critical section outside of the shear reinforced zone. The second option is to apply the check for minimum reinforcement for drift. I'll explain both of these now. For the first option, historically the program has checked a critical section that is rectilinear. So we have 4 straight sides. The program would check that out d/2 spacing until you hit what we call a layer that requires no reinforcement. So maybe this is layer 10, and layer 10 yields the need for 0 amount of area of still. Let's say that's the value for area of still. In the implementation with this new option of considering this critical section, the program determines that location. It then checks it a second time using the octagonally shaped section. So the program has input. If these are our rails, for example, this is an interior condition. These might be the stud rails. I'm just showing 2 for purposes of the demonstration. The user can enter the edge distance to the rail or stirrup line from the face of column. The critical section would then be based off of this shape here. Okay, and the program would check this layer again. So if this is layer 10, the program checks layer 10 again, and depending on whether or not the stress on that critical section, which is the least critical section based on this arrangement of stud rails, if that stress is less than 2 square root of f prime c per code, the program would no longer check additional rails and it would be acceptable. If it's greater than 2 square root of f prime c, the program would then check multiple rails of this octagonally shaped critical section. So you might have an additional, let's say, if we go all the way out to here, 15 rails, or 15 layers rather. So the program would check additional critical sections with this new shape until that stress of 2 square root of f prime c is met, if it's less than or equal to that stress. That is what this option is for. The user can select this. If selected, it will check those critical sections. If not, it would actually check it as previous versions of the implementation were done. This new option is meant to support the explicit need for checking the least critical section per ACI 318.14. The second check is applying minimum reinforcement for drift, and in this case the program will determine a distance 4 times the slab thickness. Any critical section that falls within this distance, this might be 5, 4, 3, 2, 1, any critical boundary within that 4H, the program will determine whether or not the area of still is greater than or equal to 3.5 square root of f prime c. If not, it will add more rails for that particular provision of the code. Now the best way to check these two options is really in the details of the output. The program produces reinforcement, which doesn't obviously provide a lot of detail into the back-end calculations, but if we take this slab and I run through the shear check for the slab, over here in the design results, if I select a strength combo under punching shear, I can produce, for example, a stress check. Grid D2 requires reinforcement, and I can easily check the graphical arrangement of the reinforcement here. I could compare this output to turning off or on the octagonally shaped section, which is again the new option, or the seismic drift section. So if we look at the details of this actual design of this column, we can go back to reports, punching shear, XLS, this gives us more detail into what's actually happening at that section. If we look at grid D2, just navigate down, that's this block right there. We can see that this is the critical area. Column L is the critical section area. You can see that builds and builds and builds until section 5. At section 5, the critical area is 1425 square inches. It then drops down to 1226. That indicates that is the location where we transition from a rectilinear to an octagonally shaped section. And then there's additional checks made beyond that, all the way from 6 through 14 are required in order to get the stress less than 2 square root of f prime c. And that affects the amount of reinforcement being added to this particular design. If you go to the stress check, there's also an indication here that would show us something similar. We can see the program checks the stress based on some allowable, which is indicated in this column here. If we go all the way back up, this is the allowable stress column. I'll widen that so it's easier to see. And once you get down to section 5 and 6, at 6 we get 0.095, and that's actually repeated. That indicates that this is 2 square root of f prime c. That becomes the allowable stress and the target that we're trying to meet with those octagonally shaped sections. The third indication would be the area of steel required. Coming down here to column D2 for strength, at section 5, the amount of reinforcement needed based on a rectilinear section is 0. At that point, we recheck it based on the octagonally shaped section, and there's additional reinforcement needed out to layer 14 until we get back to 0, meaning we meet that allowable stress condition of 2 square root of f prime c. The last thing we're going to discuss is the ability to check long-term losses using Felt 3D within the PT Shop module for ADAP Builder, and also a new tendon shape that can be set as a character for the model tendon. Coming back to our model, if we go to this option to show tendons and we double click on a tendon, there's now 3 modes of drawing the tendon, or how it's represented as an element. There's straight line representation, spline, and also fillet. This fillet / radius entry allows the program to combine really just a radius fillet along with straight segments for representing the tendon and the in-plane sweep of a tendon. So that's new for the program. If we look at stressing, under the post-tension design option, there's effective force, calculated force. Those 2 options have been in the program for a while. We get down here to long-term losses. There's an estimation of long-term loss if the option for calculated force is enabled. This estimation is only applicable when you have the PT Shop module turned off. In other words, the option for explicit calculation of long-term losses is disabled without the ability or the functionality of the PT Shop module. So if I go ahead and I close the program, okay, we're going to reopen Builder, and we're going to reopen Builder now with this option for PT Shop / Felt. I'll just reopen that one model. And under tendon now, there's a few new options here under the shop drawing module. Number 1, again, if we go to one tendon or a group of tendons, I can double click on any tendon and change this now to calculate explicit losses for that tendon. I could do this for all tendons in a model. If I select, for example, all tendons in this particular slab, I can modify those tendons. And we're first going to designate these as calculated force, and we're going to actually calculate, instead of estimating, we're going to calculate the long-term losses based on these properties. This is similar to running individual tendons in ADAPT Felt, but just batch processing losses for these tendons. That sets all of my tendons up to be calculated for losses. If we go back to tendon, I can now run the friction elongation calculation of those tendons, and I can produce reports using the Felt 3D report option for a group of tendons or an individually selected individual or multiple tendons. If we use the pull down here for Felt 3D report, this allows for single strand report, which really just indicates the losses for one strand even if a group of tendons is modeled. So for example, if this is set to 7, the same shape would be indicated for all 7 tendons, and we may only want to calculate losses for one of the strands, so that allows us to do that using the single strand option. If you go to reports, under tendon reports, you can also invoke those reports here from the PDF report option for the tendon element. If there are any questions relative to any of the new features for Adapt Builder 2019, please contact support@adaptsoft.com. Thank you.